Hello everyone. We are now going to go over some of the basics in flow cytometry. So once your sample is prepared and it is run in the equipment or in the instrument, and we start getting the data on the cells, or which we call events for flow cytometry, we have to analyze it. And once we analyze it, and we use something called gating to kind of use different characters of the cell, like its expression of certain markers, its intensity of expression of certain markers, and its forward and side scatter properties. And we use all those information to identify the cell populations. So let's go over some of the basics of that. So let's start with gating strategy. Almost always in HIMPATH, when you see a flow cytometry plot, it usually starts with the CD45 versus site scatter. It's like the Bible for flow cytometry. So some labs have CD45 in the x-axis, some have it in the y-axis. But for all practical purposes, all our flow plots in this book is going to be having CD45 in the x-axis. So that's how our illustration in the gating strategy is also. So here we have CD45 in the x-axis, side scatter in the y-axis. Now CD45 is is a marker that is expressed by almost all of the cells of hematopoietic lineage, except some. We'll see those exceptions. So that is a marker that we use so that we can eliminate all other contaminant cells. For example, if this is a bone marrow that has metastasis or any solid tumors, so we can get rid of those cells by gating on just the CD45 positive cells. Also, if it is a tissue specimen, again we can get rid of those metastatic cells or tumor cells or any epithelial cells or other debris or fibroblasts or endothelial cells. All those things we can get rid of by using CD45. That is the reason we use CD45. And a side scatter is the light that is scattered at the 90-degree angle by the cells when they pass through the fluorescence laser. So that the things that contribute to side scatter in a cell are the cytoplasmic granularity and the complexity of the cell, like the nuclear contour. For example, lobulated cells like neutrophils will have both granules and they will have some complexity to their nucleus, so which will scatter the light in different directions, which is caught by these diodes and produces the pulses, and that's what we get registered from the flow cytometry instrument. So more the granularity and complexity in the cell, more the side scatter. So if we see the CD45 expression, the brightest CD45, that is in the right end of the x-axis, is where the cells that express bright CD45 are going to sit. And based on their side scatter, the ones with low side scatter are the lymphocytes. For example, lymphocytes have no, obviously nothing in the cytoplasm for granularity, and almost their cytoplasm is so scant and their nucleus is so uniform and round, so they don't scatter much light. So they sit down here and they express the brightest CD45. So this is called the lymphocyte gate. Low side scatter, bright CD45. And the cells that sit here are lymphocytes, including lymphoma cells, especially the cells with the small mature lymphoid cells, for example, CLL, SLL, or some mantle, marginal zone. So all those cells will sit here. Even some large granular lymphocytes will sit here. Sometimes they can be either touching the other gates, like in the monocyte gates, or they can even creep into the blast gate a little bit. The gate that is just above the lymphocyte gate, it's called the monocyte gate. So monocytes sit here because they have increased side scatter because they have more cytoplasm, and they do have contents in their cytoplasms that can scatter light, and they also express the bright CD45 just like lymphocytes. So that is the monocyte gate. So other than monocytes, monoblasts can sit there, and sometimes dysplastic granulocytes can creep there because dysplastic granulocytes, as the name suggests, they are dysplastic, so they lose the granules, and also to some extent they lose their the lobation, so they can kind of have low side scatter and they kind of creep into the monocyte gate. Not they don't have that bright CD45, but you can see some creeping in there. And other thing you have to remember is in hairy cell leukemia, there is cytoplasmic projections which can increase the side scatter of those neoplastic lymphocytes. So they end up sitting in the monocyte gate sometimes. Sometimes you will see a continuous population going from the lymphoid gate into the monocyte gate. The other gate here is where majority of the cells in a normal sample sits in, like for normal peripheral blood or bone marrow. So these are the granulocytes. It includes both immature granulocytes and eosinophils. So you'll have your promyelocytes, myelocytes, metamyelocytes, bands, neutrophils, and eosinophils sitting in this gate. So they have a slightly dimmer CD45 than lymphocytes and monocytes, and they have very high side scatter, especially eosinophils. They have the highest side scatter, and they also have brighter CD45 than neutrophils. And other than normal maturing granulocytes and mature granulocytes, you can see blasts of acute promyelocytic leukemia that can be in this gate. That is because they have a lot of granules, including R rods, so they scatter a lot of light. So they kind of go up all the way in terms of side scatter. And just below the granulocyte gate is your blast gate, this one. And this has a dim CD45 compared to lymphocytes and monocytes, and they have low side scatter. And in this gate, other than blasts, you also see basophils and plasmacytoid dendritic cells. And there are markers like CD123 and HLA-DR to differentiate them. And sometimes neoplastic plasma cells can also sit there. And just below the blast gate, sometimes even a good separation is not possible. Very close to the blast gate, we have the hematogones gate, and they have hematogones and sometimes B and T lymphocytes. Many times actually, the B and T lymphocytes can sit here. Not lymphocytes, lymphoblasts. B lymphoblasts sometimes can have even very dim CD45 that you have to include some cells that are negative for CD45 to your gate. And sometimes LGLs can sit here. And the one that has like very low or almost negative CD45, we call this as erythroid gate. So that has low side scatter, dim to negative CD45. So obviously, nucleated red cells, which are only the early hematopoietic progenitors or the early pro-erythroblasts can have CD45, and then once they start maturing, they lose their CD45. So they are all almost negative. So erythroblasts, that is neoplastic erythroblasts and neoplastic megakaryoblast, they are all usually CD45 negative, or they have very dim CD45. And neoplastic plasma cells lose CD45, so they can sit here. And sometimes lymphoblasts, like I said, especially in BALL, they can sit here. So then once you get your population of interest, then we can also use certain markers to isolate the population that we need. Like for example, we know that B cells express CD19 throughout their life, like from immature stage to maturation stage. So if you want to isolate anything in the B lineage, you can use CD19. Similarly, for T lineage, you can use CD3 and CD7. If you're using, if you want to isolate the mature T cells, you can use CD3. If you want to include this immature cells, then you can include CD7. If you want to isolate plasma cells, then we go for the cells that express the brightest CD38. For mast cells, we use the brightest 117 expression. And if you want to isolate your monocytes, we go for CD14 and 64 expression. And for granulocytes, if you want to separate the maturing immature granulocytes from the mature neutrophils, then you can use CD10 and CD16. So we have markers. You can use CD34 for blasts. So subsequently, you can use these markers to isolate the population that you want to study further. Now let's start going over some of the basics of flow cytometry interpretation. So the data that the instrument collect from all these events that are going through its going through its flow channel, that has to be presented in some way for us to, have a visual experience of what's going on with these cells, and to understand and to interpret what is wrong in which population. So this data can be presented in multiple ways. For example, they can be presented as histograms, or they can be presented as dot plots, or contour plots or density plots. But the most common ones that most hematopathology labs use are the dot plots. So dot plots means each and every cell or the event that went through this process in the instrument is presented as a dot. So for example, if you are analyzing a peripheral blood for leukemia, your lab is going to set up a few tubes. Some labs set up one tube for B cell markers, one tube for T cell markers, one or two tubes for myeloid markers. It depends, whatever your lab prefers. So let's see what the tubes actually mean. So basically, let's say your flow cytometer has the ability to analyze 8 fluorochromes at a time. So that's what we commonly call as an 8-color flow cytometer. We have different color flow cytometers. We have 10, 12, 16, 18. It has gone so wide these days. But for example, if your flow cytometer has the ability to analyze 8 fluorochromes or 8 antibodies at one time, that means you can in each tube you can use up to 8 antibodies, or the antigen and antibody and the fluorochrome combination, basically. So let's say in one tube you have your myeloid markers, and one tube you have your monocytic markers like 11B, 64, 14, and 56. So like that, we have 4 or 5 or whatever number of tubes that your lab wants to set up, or whatever the protocol is. They set it up, and then after they run the sample in the instrument, we get the data. And then each and every cell that has that was subjected to, let's say, 8 antibodies in one tube, we will know the relative expression of each of these antibodies, right? So for example, in one tube, you had 34, 117, DR, 13, and 33, 15. Then you can compare the expression of any of these markers between themselves in that tube. So for example, you can compare the particular population. Let's say here it is the blast population. You can say if the blast population is positive for 34 and 117, you can see if it is positive for the same blast population is positive for 34 and HLA-DR, 34 and 13, HLA-DR and 13. So you can have different combinations and look for the relative expression of each of these markers in that tube. But if you have 13 in tube 1 and CD64 in tube 2, you cannot compare those two in the same population, because you have to have those markers in the same tube for you to see this to see the relative expression in one tube. So that is one thing you have to remember. So you have to design your panel that way so that you have something in each tube to tell you what the population of interest, what your population of interest is. So and then in for example, in this plot, when we call something as positive, it means that it is expressing the marker in that axis. For example, we also have these lines in many of our graphs. Those are the lines that are drawn to divide the plot into quadrants. So we have like 4 quadrants here. So, and we have the x-axis labeled with 1 fluorochrome and antibody, and the y-axis labeled with 1 antibody and fluorochrome. So if an event sits here, like for example, these dots that are here, it means that this is positive for this marker that is in the y-axis. For example, here it is 138, but it is negative for the kappa. So these quadrants help in determining the positivity or negativity of these cells. For example, if they sit here, it means that they are positive for both 138 and kappa. If they are here, they are positive for kappa, but negative for 138. And if they're here, it means they are negative for both 138 and kappa. So these lines basically separate the positive from the negative population. So for example, on the x-axis, anything that falls on the right of this line is positive for the marker in the x-axis, and anything that falls to the left of this line is negative for the marker in the x-axis. Similarly, for the y-axis, anything that falls above this line is positive for the marker in the y-axis, and anything that falls below this line is negative for the marker in the y-axis. So all of these are positive for 138, and all of these are negative for 138. All of these are positive for kappa, all of these are negative for kappa. So how are these lines drawn? So when they set up your QC, or when they validate the specimen, validate your the instrument initially, they adjust these lines based on some control populations, or they use fluorospheres that are commercially available, and they kind of set this for optimal optics and compensation, and they derive these lines. Sometimes we can move these lines a little based on the aberrance, like on the neoplastic population, but we normally don't touch these lines for normal populations. And so these are the dots, and that's why this is called a dot plot. Now, when we talk about the expression of an antigen, we use some words like bright expression, moderate expression, it is uniform, or it is partial. So now let's see what that means. So this is another dot plot that you see here with quadrants, and we have CD33 in the x-axis, CD34 in the y-axis, and whatever you see next to the antigen, that's the fluorochrome that is used. For example, here CD33 is tagged to PE, and CD34 is tagged to Percy P Psych5. Now, this is the population of interest. So this population is composed of, I don't know how many dots. There are like too many dots there. So each dot is one cell. So this is the population. Let's say this is 34 positive. So let's say this is our blast population. So it is uniformly positive for CD34. So we'll say positive, and it is only partially positive for CD33. So this line also helps if you have, some labs don't make those quadrants, but if your lab uses those quadrants, then it also helps determining, the partial expression or uniform expression. So all of this is uniformly positive for 34, but it's partially positive for CD33. So that's what the term partial means. And now usually when a population, when 20% or more cells in a population expresses a marker, we call it positive. For example, here 60% of this population is positive for CD33. So CD33 is positive, but giving the description like kind of more accurately represents what you see. So if you say partial, it is more accurate description of what you see in the flow plots. And again, this one, we can see that, this CD7 here is pretty bright. Like it's kind of away from the quadrant line that separates negative from positive, and it's very nicely, uniformly, brightly positive. Whereas CD3 is like moderately positive. Like it's, if it is sitting here, we'll call it bright. Here it is moderately positive. So that's what the moderate or bright that means. And if majority of CD3 is here with only like 25-30% that crosses the positivity line, then we'll call it dim positive. That's what the meaning. That's the meaning of bright, dim, moderate. Many a times you will see a spray of cells going into the other gate, and you have to be very cautious about it. Sometimes it could just be contamination from the neighboring gate. Like for example, in the blast gate, you can have cells creeping from the lymphoid gate, like the large NK cells. So they'll be positive for 7, negative for 3. So they can sometimes creep into your blast gate. So you need to be very cautious of that population, but sometimes they can be a separate blast population, or sometimes it could even mean aberrant expression. But see what percentage it is, and see also, if you want, you can even gate this separately and see what other markers this one expresses to kind of correlate if it is significant or not. But anything that you see like a spray that is so distinctly away from your main population, most likely it is just contamination from other gates. But if you see that this is persistently, you see that in many other plots, and you see that it is kind of expressing something specific, you can gate it and identify what population it is. And if you think that that is a separate population of aberrant cells, then it is worth working it out. So, and one more thing you have to always remember is flow cytometry is never used for obtaining the numbers. Your numbers are from the differential count. For example, if you want to get the blast count, you have to use your differential count to get that number. You don't use, if your flow cytometry say this is 25% blast, don't use that number for determining whether it is acute leukemia or not. You have to use your differential count to say it is acute leukemia or not. The purpose of flow cytometry is only to phenotype the population of interest. So if you see blasts in the peripheral blood, you do flow cytometry to see what lineage those blasts belong to and what aberrant markers they express. That's the job of flow cytometry. It's not supposed to be used for the purpose of quantitation of numbers, because the specimen goes through a lot of processing and we infuse a lot of artifacts into it. So the numbers are, although closer to the real life in many times, but it's not reliable. And also sometimes when you cannot depend on this line that makes the quadrants, or sometimes you're not sure if this expression by this population should I consider it positive or negative, then you can always use your control population. For example, if you want to know if this CD3 is positive or negative, you can always compare it to your background T cells, because you're going to have some T cells in the background. You can pull that into your into a plot to see if this matches the intensity of the CD3 of your T cells, then you can call it positive. If it is not matching, then you can call it negative. So that relative expression also helps sometimes. That we often use that in cytoplasmic CD3 or cytoplasmic MPO, because those markers tend to be more noisy and can have an artifactual appearance of being positive. So we often compare them with the normal neutrophils or T cells in the background to decide whether it is positive or negative. So that's the basics of flow cytometry interpretation. And when we go through each of our chapters, we'll discuss more into the specifics of, and we'll also learn more and more about interpretation. Thank you.